close your eyes and picture this. You're standing on Earth, looking up at the sky, but something's wrong. The sun isn't a bright disk anymore. It's a wall of fire that fills the entire horizon, stretching in every direction. The sky itself is glowing red-orange, and you realize with horror that you're not looking at the star. You're inside it. This isn't science fiction. Stars like this actually exist, stellar monsters so incomprehensibly massive that our sun is a grain of sand by comparison. I'm talking about hypergiant stars, and today we're going inside them. But before we dive in, quick question. Do you think our sun is big or small compared to other stars? Drop your answer in the comments. In our first episode, we talked about what would happen if gravity just stopped. We watched Earth tear itself apart and spiral into chaos. But gravity doesn't just hold planets together. It's also responsible for creating the most magnificent and terrifying objects in the cosmos, stars. Let me refresh your memory on scale. Our sun has a diameter of about 1.4 million kilometers. That's 109 times wider than Earth. Sounds massive, right? Wrong. Compared to red giants like Betelgeuse, our sun is pathetic. Betelgeuse is roughly 700 times larger in diameter. If you placed it where the sun is, it would swallow Mercury, Venus, Earth, Mars, and reach past the asteroid belt. We'd be vaporized instantly deep inside the star's outer layers. But Betelgeuse, still not even close to the biggest. The true monsters, the hypergiants and supergiant stars, make Betelgeuse look modest. We're talking about stars with radii over 1,700 times that of our sun. Stars so large that light traveling at 300,000 kilometers per second would take hours just to cross from one side to the other. Stephenson 218, one of the largest known stars, has a radius estimated around 2,150 solar radii. Though measurements vary due to the immense difficulty of accurately measuring such distant objects, these are the monster suns, and they don't play by the same rules. So how does a star get this big? It all starts in the same place: giant molecular clouds, vast, cold regions of space filled with hydrogen, helium, and dust. These clouds can be hundreds of light years across and contain enough material to birth thousands of stars. They exist at temperatures just above absolute zero, typically around 10 to 20 Kelvin, and have densities of only a few hundred to a few thousand molecules per cubic centimeter. That sounds like a lot, but it's actually a better vacuum than anything we can create in laboratories on Earth. Here's where gravity comes in again. Inside these clouds, tiny fluctuations cause gas to start clumping together. These fluctuations can be triggered by various events: a nearby supernova shockwave, the collision of two clouds, or even the gravitational influence of passing stars. As the clump grows, its gravity pulls in more material. The gas compresses, heats up, and as more and more mass accumulates, the pressure and temperature at the center rise dramatically. When the core temperature reaches about 10 million Kelvin, something magical happens. Hydrogen atoms, stripped of their electrons by the intense heat and pressure, begin slamming together with enough energy to overcome their electromagnetic repulsion. They fuse together, forming helium and releasing tremendous amounts of energy in the process. Nuclear fusion begins. A star is born. But here's the key: mass decides everything. A star's mass determines its temperature, luminosity, color, lifespan, and ultimate fate. Think of it like this: stars are in a constant battle between two forces: gravity pulling inward, trying to crush the star, and radiation pressure from nuclear fusion pushing outward, trying to blow it apart. This balance is called hydrostatic equilibrium, and it's what keeps stars stable. For a star like our sun, this balance is remarkably stable. Fusion in the core produces just enough outward pressure to counteract gravity. The sun will maintain this equilibrium for about 10 billion years total. It's currently about 4.6 billion years into that lifetime. It's in what astronomers call the main sequence, the longest and most stable phase of a star's life. But when a star forms with 50, 100, or even 200 times the mass of the sun, everything changes dramatically. More mass means more gravity, which compresses the core harder, cranking up the temperature and fusion rate to extreme levels. These massive stars burn furiously, converting hydrogen to helium at a rate millions of times faster than our sun. This creates immense radiation pressure that inflates the star's outer layers to colossal sizes. The most massive stars have core temperatures exceeding 40 million Kelvin, compared to the sun's 15 million Kelvin. This exponentially increases fusion rates through what's called the CNO cycle, the carbon-nitrogen-oxygen cycle, rather than the proton-proton chain reaction that powers our sun. In the CNO cycle, carbon, nitrogen, and oxygen act as catalysts for hydrogen fusion, making the process much more efficient and temperature sensitive. A small increase in temperature leads to a dramatic increase in energy production. The result? A hypergiant star that's not just bigger, but fundamentally different in almost every way. These stars emit so much radiation that they're constantly blowing their outer layers into space through powerful stellar winds. Some lose more mass in 1,000,000 years than our sun will lose in its entire lifetime. Think about this. The sun will live for 10 billion years, but these monster stars, they'll be dead in just a few million years. Some of the most massive might only last 1 or 2 million years from birth to death. It's like comparing a human lifespan to a mayfly. Let me know in the comments, would you rather live long and dim or burn bright and fast? Let's meet some of these cosmic giants. Fair warning, these measurements are incredibly difficult to make and constantly being refined. Stars at these distances don't appear as disks even in our best telescopes. They're just bright points of light. Astronomers use indirect methods like luminosity, temperature, and spectral analysis to estimate their sizes. They look at the star's color, which tells us its temperature. They measure its brightness and distance to calculate luminosity. From temperature and luminosity, they can estimate radius using the Stefan-Boltzmann law. But all these measurements have uncertainties, sometimes quite large ones. R136A1. Let's start with the heavyweight champion of mass. Located in the Tarantula Nebula in the Large Magellanic Cloud, 163,000 light-years away, R136A1 weighs in at roughly 196 times the mass of our sun. This makes it one of the most massive stars ever discovered, though it may have been even more massive when it formed. Estimates suggest it could have started with as much as 300 solar masses. But here's what's truly insane. R136A1 produces as much light as 4.6 million suns combined. Let that sink in. 4.6 million. If you replaced our sun with R136A1, Earth wouldn't just be vaporized. Our entire planet would be obliterated by radiation in seconds. The star is so luminous, it emits most of its energy as ultraviolet light, which our eyes can't even see. If we could see ultraviolet, R136A1 would appear blindingly bright even from Earth, despite being in another galaxy. R136A1 has a surface temperature of around 53,000 Kelvin, nearly 4 times hotter than the Sun's 5,500 Kelvin surface. The star is so hot that it's actually classified as a Wolf-Rayet star, an extremely rare type characterized by intense stellar winds and high temperatures. It loses mass through these stellar winds at a rate of about 1 solar mass every 22,000 years. That might not sound like much, but consider this. The sun loses less than 1/1000th of a solar mass per year through its solar wind. R136A1's expected lifespan? Maybe 2 million years. It's already middle-aged in stellar terms and will die soon, cosmically speaking. When it goes, it will likely produce one of the most energetic supernova in the universe and leave behind a massive black hole. UY Scuti. Now let's talk about size. UY Scuti is a red supergiant located about 9,500 light-years away in the constellation Scutum. While its mass is only 7 to 10 times that of the Sun, its volume tells a completely different story. UY Scuti has a radius estimated at 755 solar radii, though some measurements suggest it could be as large as 1,200 solar radii. The uncertainty comes from the fact that red supergiants don't have well-defined surfaces. Their outer layers are so diffuse and extended that it's hard to say exactly where the star ends and space begins. If you placed UY Scuti in our solar system, it would extend beyond the orbit of Jupiter. Its volume could fit 5 billion suns inside it. 5 billion. And yet, because its outer layers are so tenuous, its total mass is only 7 to 10 solar masses. UY Scuti is in its death throes. It's exhausted the hydrogen in its core and is now fusing heavier elements in shells around a degenerate core. The star has expanded enormously as it evolved off the main sequence, and its outer layers are so diffuse that the density is lower than Earth's upper atmosphere. In some regions, it's essentially a hot vacuum. Despite this, the star still produces around 340,000 times more light than our Sun. Red supergiants like UY Scuti are unstable. They pulsate, changing size over periods of months or years. They shed mass irregularly through powerful stellar winds and occasional massive eruptions. Some astronomers think UY Scuti might actually be surrounded by a thick shell of dust and gas that it's blown off in previous eruptions, which could make it appear even larger than it actually is. Stephenson 218. This is potentially the largest known star by radius, though measurements are highly uncertain. Located about 19,000 light-years away in the massive star cluster Stephenson 2, this red supergiant has an estimated radius of 2,150 solar radii. If you place this monster where our Sun is, its surface would reach nearly to the orbit of Saturn. A passenger jet traveling at cruising speed would take over 1,100 years just to circle this star once. Light, traveling at 300,000 kilometers per second, takes about 8 hours to travel from one side of Stephenson 218 to the other. For comparison, light takes only 4.6 seconds to cross the diameter of our Sun. At this size, the star's outer layers are so tenuous that they're nearly a vacuum by Earth standards, yet still produce enough light to outshine our Sun by hundreds of thousands of times. The luminosity of Stephenson 218 is estimated at around 440,000 times that of our Sun. Though this too is uncertain, these measurements for Stephenson 2-18 are particularly uncertain because the star is embedded in a dense star cluster and surrounded by dust, which makes it difficult to observe and measure accurately. Some recent studies suggest it might be somewhat smaller than the original estimates, but it's still undoubtedly one of the largest stars we know of. VY Canis Majoris, I have to mention this one because it was long considered the largest known star before better measurements revised its size downward. Located about 3,800 light-years away, VY Canis Majoris is a red hypergiant with a radius of about 1,400 solar radii. It's intensely luminous, producing somewhere between 270,000 to 500,000 times the Sun's luminosity. What makes VY Canis Majoris particularly interesting is that it's surrounded by one of the most complex and massive nebulae ever observed around a star. The nebula contains knots, arcs, and filaments of ejected material, showing that the star has been shedding mass violently and irregularly. Astronomers estimate the nebula contains at least half a solar mass of material that the star has blown off over the past few thousand years. These stars all have one thing in common: they're dying, fast, and their deaths will be spectacular. Here's a mind-bender for you. Which is more impressive, a star that's incredibly massive and powerful like R136A1, or one that's unbelievably huge like Stephenson 2-18? Vote in the comments and tell me why. Massive stars don't fade quietly into the night. They die in the most catastrophic explosions the universe can produce, and they do it fast. Remember, these stars burn through their fuel at breakneck speed. They start by fusing hydrogen into helium in their cores. This is the main sequence phase, where they spend most of their lives. Though for massive stars, that's still only a few million years. When hydrogen runs out in the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. Meanwhile, hydrogen continues fusing in a shell around the core. As the helium runs out, the core contracts again and heats further until it can fuse carbon into neon and magnesium, then neon into oxygen and magnesium, oxygen into silicon and sulfur, and finally silicon into iron. Each stage produces less energy and happens faster. The hydrogen burning phase might last 1,000,000 years for a very massive star. Helium burning lasts maybe 100,000 years. Carbon burning, a few hundred years. Neon burning, about a year. Oxygen burning, a few months. The final stage, silicon, fusing into iron, lasts only a few days or even hours. Iron is the endpoint because fusion reactions involving iron consume energy rather than produce it. Iron has the highest nuclear binding energy per nucleon, meaning its nucleus is the most tightly bound. You can't extract more energy by fusing it into heavier elements. In fact, fusing iron requires energy input rather than releasing energy. So when the core is mostly iron, the star's energy source is exhausted. Once the core can no longer produce energy to support itself against gravity, catastrophe strikes. In less than a second, literally, in about a quarter of a second, the core collapses catastrophically. The temperature and density skyrocket beyond anything we can recreate on Earth. Electrons are forced into protons, creating neutrons and releasing vast numbers of neutrinos. The core shrinks from something the size of Earth to about 20 kilometers across, a neutron star where matter is packed so densely that a teaspoon would weigh as much as Mount Everest. Then comes the rebound. Infalling material from the outer layers slams into the incompressible neutron core and bounces. This creates a shockwave that races outward through the star at 10% the speed of light, ripping it apart in a core collapse supernova. For a few weeks, a single dying star can outshine an entire galaxy of 100 billion stars. A typical core collapse supernova releases about 10 to the 44th joules of energy. That's a 1 followed by 44 zeros. To put that in perspective, that's more energy than our sun will produce in its entire 10 billion year lifetime, released in seconds. Most of this energy, about 99%, is actually carried away by neutrinos, ghostly particles that barely interact with matter. The remaining 1% goes into the explosion itself and the light we see, which is still enough to briefly outshine a galaxy. The explosion hurls the star's outer layers into space at speeds of 10 to 30,000 kilometers per second. This expanding debris, the supernova remnant, spreads through the surrounding interstellar medium, creating beautiful and complex structures. The Crab Nebula, for example, is the remnant of a supernova that was observed in the year 1064. But for the most massive stars, those with initial masses above 40 to 50 solar masses, something even more extreme can happen. The core becomes so massive that even neutron degeneracy pressure can't hold it up. The force that keeps neutrons from occupying the same quantum state, which supports neutron stars against collapse, simply isn't strong enough. The core doesn't bounce, it just keeps collapsing, straight past the neutron star phase, straight into a black hole. When this happens, the normal supernova explosion might be weaker or might not happen at all. In some cases, the star might just implode, collapsing directly into a black hole with little or no visible explosion, a so-called failed supernova. Astronomers have actually observed cases where massive stars simply disappeared with little fanfare, likely having undergone direct collapse to a black hole. Some of these collapsing stars produce hypernovae or long gamma-ray bursts, the brightest electromagnetic events in the universe. These explosions are 10 to 100 times more powerful than regular supernovae. They occur when a very massive, rapidly rotating star collapses to a black hole. The rotation causes the star to form an accretion disk around the newly formed black hole, and powerful jets of matter and radiation shoot out along the rotation axis at nearly the speed of light. If one of these jets points toward Earth, we see it as a gamma-ray burst, a brief flash of the most energetic form of light. These bursts can last anywhere from a fraction of a second to several minutes for long gamma-ray bursts, and they're so bright that we can detect them from across the observable universe. A gamma-ray burst in our galaxy, with its jet pointed at Earth from within a few thousand light-years, could strip away our ozone layer and cause a mass extinction event. Fortunately, this is extremely rare. We detect long gamma-ray bursts maybe once a day from the entire observable universe. So, sleep easy tonight. The monster stars are out there, burning bright and dying young. But they're not coming for us. Monster stars, the biggest, brightest, most short-lived objects in the universe. They live fast, die young, and leave behind black holes, neutron stars, and the raw materials for planets and people. Our sun is just a tiny yellow dwarf by comparison. Stable, long-lived, unremarkable in almost every way. But that's exactly what makes it perfect for us. We need a star that won't explode or blow away its planets with powerful stellar winds. We need a star that will stay on the main sequence for billions of years, providing steady energy for life to evolve. We need boring. And I, for one, am grateful for boring. But speaking of black holes and neutron stars, those remnants of dead monster stars, what are they really? What happens if you fall into a black hole? What's it like inside a neutron star, where a teaspoon of matter weighs as much as a mountain? And are there even stranger objects lurking out there in the cosmos? Quark stars, strange stars, or things we haven't even imagined yet. That's coming in episode 5, when we explore the absolute weirdest, most extreme objects in the universe. If you enjoyed this deep dive into the largest stars in the universe, smash that like button and subscribe so you don't miss the next episode. Hit that notification bell too. We're going to explore objects so extreme they break the normal rules of physics. And trust me, it gets absolutely wild. Drop a comment and let me know, what space topic do you want me to cover next? The death of the universe? Rogue planets drifting through interstellar space? The search for alien life? Your suggestions help me create the content you want to see.